Hi everyone, I'm Xiwei from Shanghai Jiao University. I'm excited to present our work about eBPF verification toolchain here. eBPF is a powerful technique for Linux kernel. It allows developers to add new functions or modular to the kernel flexible. The safety of this additional kernel is tested by an eBPF verifier. Ideally, the eBPF verifier should only reject the truly unsafe programs, those that maybe crash the kernel or violate some safety guarantees. But in reality, today's verifier rejects any programs it cannot prove safe. Programs with complex loops are normally rejected by Linux verifiers. It seems that the Linux verifier is not powerful enough to find out why our programs are actually safe. One may wonder if the verifier should use more advanced verification technique so that the false positive rate can be lower. Actually, Microsoft and their PREVAIL verifier did try that by employing abstract interpretation. To be honest, PREVAIL achieved a lower false positive than Linux verifier, but the false positive rate is still high, and it has higher resource consumptions because it uses these three to solve some constraint solving, which is a large SMT solver. So even use the most advanced verification technique, the verifier is inevitable to generate a lot of false positive. The real problem is about the design of the verifier. Currently, the verifier only takes programs but nothing else as input. Under this setting, it is impossible to simultaneously achieve 0 false positive and 0 false negative. As a result, verifier designs must make a trade-off between false negatives and false positives. Therefore, since eBPF verifiers is 0 tolerance to false negative, the false positive side has to be sacrificed. The design problem of the eBPF verifier is the most important problem that motivates our research. Let's see another problem. Another problem of eBPF verifier is about its feedback to developers. The current Linux verifier's feedback is difficult to interpret. Even highly experienced developers often spend a lot of time to figure out why their programs are rejected. The core challenge is to map the bytecode output to the original C code. Consider the compiler optimization maybe change the structure of the program. The mapping is time-consuming and error-prone. One may think about verifying the C program directly. This shows one of the feedback in one of the C verifiers. And a typical C verifier can figure out the error lines, which is shown in the red, and the error message is printed in the output black. So, while the C verifier provides better feedback. However, using C verifier will cause significantly higher resource consumption. Additionally, even after verification, C programs still need to be compiled before they can be loaded into the kernel, which means it cannot defend against direct manipulation of the compiled machine code. In summary, current eBPF verifiers face two challenges. They generate too much false positive, and the feedback is not friendly enough for developers. To address these two challenges, we designed the new eBPF verifier VEP. For the first problem, VEP requires users to provide additional annotations. And for the second problem, VEP adopts a two-stage verification strategy. Developers can refine their codes using the C verifiers by feedback, while the kernel enforces safety via bytecode-level verification before loading. Let's see how VEP works. VEP is about three components: a C-level verifier, an annotation-aware compiler, and a bytecode-level verifier. VEP begins with a C-level verifier, VEP-C. VEP-C will initially check on the user annotation C program. And VEP-C will provide an ID support like what we see before, and for better human feedback, developers can refine their code iteratively using VEP-C until it passes our verification. During this process, C verifier will use advanced verification technologies to fill or proof gaps, and it will generate lots of heavily annotated C programs that it's enough to show its correctness. And if someone needs to check the program safety based on these heavily annotated details, it is simple. The next, the VEP-compiler will compile the heavily annotated C program into annotated eBPF bytecode. In this process, relevant annotations, and it will also undergo corresponding compilation passes. Finally, VEP uses a bytecode-level verifier to perform a final verification. At this stage, the bytecode verifier will check that the compiled bytecode program can pass all the safety checks according to the compiled annotations. Due to the existence of sufficient annotations, this verifier only needs very little computation resource. In our design, the VEP-C and the VEP-compiler is in the user space, and the VEP bytecode verifier is in the kernel space. Here we use an example to show the whole process. Consider an eBPF program handling XTP packets. Here we show the control flow graph of the program in the left. The key challenge of this program's verification is to make sure there is an Ethernet header in the package after the first if condition, the Ethernet plus 1 greater than the data end. Let's first see what is the XTP packet. For an XTP packet, the data field points to the start of the packet. The data end field marks the end of the packet. And we ignore the other field that is not relevant to this example. And the Ethernet header is at the top of the XTP packet. If there are enough memory, we can find it. We use store XTP to represent the whole memory stores as the program variable XTP. And in this example, it is a pointer. So we can write down the function specification, which enables that the input of the function is a XTP memory block. And the output of the function is also a XTP packet. And the packet's memory block remains unchanged, and all operators in this function is safe. And the VEP-C starts with the precondition store XTP. Then, before the load the XTP data end, the VEP will split the predicate store XTP into the store chars, and it represents from the pointer XTP data to the XTP data end, there is a memory. And before another two assignments, we check the code up to the first if statement. And we can see we have successfully declared and initialized the local variable data and the Ethernet. And then, if the first if condition is true, it comes to the return command. And VEP-C will check the return state is valid, which means the current assertion can automatically entail the post condition. And this proof can be simply done by fold the store XTP for the precondition, or the unfold the store XTP in the post condition. If the if command becomes false, and to load the Ethernet hproto, VEP-C also need to split the memory block from the XTP data to XTP data end and get the memory of the Ethernet header. And it is split into the 4 parts. As the if condition permits that the length of the memory block is longer than the length of the Ethernet header, the split operator is valid. And the rest is similar, and we'll admit here. Till now, we get the heavily annotated eBPF-C programmers. The red small square and the blue, the red small square and the blue squares are the annotations generated by VEP-C. And the red big black block represents the validation check for return command. After that, the heavily annotated C programs will be compiled by the VEP-compiler. We have implemented a very simple compiler that does not contain too much optimizations, but contains the most typical and representative compilation steps like liveness analysis and the register allocations. VEP-compiler will compile C program into bytecode programs and convert annotations at the same time. Here we use another example to show the conversion. This is a function from GCC stringlib. After the program gets compiled, the input parameter P1, P2, and N will be compiled into the R1, R2, and R3, the register. And the chars P1, N, L1 represents that a char array of length n stores as a program variable P1, which data list is L1. And after conversion, it will become the char array stored as the value of the register R1. Here is R1's value. And the register R6 to R9 will be the same after the function because of the promotion of the eBPF. If we go back to our XDP example, the compilation result is shown here. Although the control flow graph of the program is similar, but the code in each block becomes bytecode, and the annotations in each square also become bytecode annotations. Here, as because of the annotation is too long, so we admit some here. After VEP bytecode check, the program is allowed to load into kernel. After going through the process, we need to answer the questions we present at the beginning. Let's start with the user feedback. How do users find bugs in the development? As we saw before, we take advantages of the C verifier capability, allowing it to identify where and why an error occurs right at the C stage. VEP also provides a similar IDE support and gives the feedback like other C verifier. Next, regarding the choice of the verifier, why doesn't VEP just use the bytecode verifier alone? It is because of the feedback. So why doesn't VEP just use the C verifier alone? Because the C verifier cannot run in kernel space due to its overhead. But user space operation opens safety holes. Verified programs can be added by malicious users. To address this, VEP's bytecode verifier serves as a final safeguard by verifying whether the annotations match the actual code. As for false negative and false positive, in some sense, VEP achieves both 0 false positive and 0 false negatives. First, run program will not have a correct annotation to cheat our verifier. This is obviously 0 false negative. Next, correct programs with wrong annotations will be also rejected. Fundamentally, programs develop software will have an implicit correctness proof about their program in his mind. As established by Hoare logic and separation logic research, such proof can indeed be formally expressed through appropriate code and annotations. Therefore, every correct program will exist a correct annotation to pass VEP. This is what we call 0 false positive. And this shows some evaluations. In order to evaluate our toolchain, we get some programs from the Linux and PREVAIL datasets for evaluation. You can see that the Linux verifier and PREVAIL will also have false positive on their own datasets due to version issues, like they here and here. VEP was able to go through these examples, and the cost was as expected. VEP-C will cost more resource, and the VEP bytecode will cost less. For another, we also selected string manipulating functions from GCC library and some unsafe programs as test cases. Both Linux verifier and PREVAIL produce false positive on the string functions. And VEP, perfect accuracy on string functions, producing 0 false positives. Furthermore, the 3 verifiers both successfully identified and rejected the unsafe programs as what we expected. Finally, let's look at the annotations needed. VEP requires a relatively modest number of annotations to verify programs efficiently. For example, in the Linux samples, with 618 lines of code, only 76 assertions were needed. This is what we call annotations. And it will generate 64,840 proof obligations. It is what we call proof gets, and it will be added into the heavily C program. This indicates that a small number of high-level annotations can generate sufficient proof gap. In summary, we have developed a novel eBPF verification framework that addresses 2 key limitations of existing verifiers: insufficient verification power and unfriendly feedback. VEP's solution combines user-provided annotations with an innovative 2-stage verification architecture. Through our experiments, we have shown that VEP successfully achieved our design goals. That's all. Thank you. Any questions?